like to begin by introducing you to what some have called the new bionic man. This is a robot that was put together by a team of scientists and engineers last year by collecting together all of the different medical devices, implants, prosthetics that are either currently available for use in patients or are soon to enter clinical trial. It's amazing, right? It is a great testament to how far medical technology has come. The team estimated that they were able to recreate slightly over 50% of the body parts in this robot. But what about the 50% that they couldn't recreate? What's missing? So, one important organ system is the nervous system, and it's missing here. There is no brain, no spinal cord, no peripheral nerves. So the robot cannot sense information from its surroundings, and it cannot control its own movements. It requires a person working remotely on a computer to make it move. Another important organ system that's moving is the gastrointestinal system. There's no stomach, there's no intestines. We use that organ system so we can extract chemical energy from the food we eat. This robot can't do it. The robot has to rely on battery packs for power. So why? Why can't we yet engineer those types of organ systems? So one of the key things that's missing are cells. Now this is an image taken using an electron microscope from a sample that my laboratory obtained of intestinal tissue. Electron microscopes are great because they give you very detailed, beautiful information about your sample. And the entire surface of this intestinal lining is covered with cells. And the job of these cells is to absorb the nutrients from the food as it passes by. You'll see the surface is undulating to increase the amount of surface area in contact between the cells and the food. It's a hard job absorbing all of these nutrients, and so as the cells age, they die. But that's okay, because as they die, that's what we captured in this, what I'm highlighting in this white circle. As they die, they round up and they slough off, but they're replaced. And in a healthy person, you replace this inner lining of your intestine once every week for your entire lifetime. So this is truly living. In contrast, this robot has no living cells. But I would submit that that's not the real reason that engineers and scientists can't recreate those types of organs. After all, we know how to keep cells alive in a petri dish. But what we don't yet know how to do very well is to create materials that can interact with the cells in an appropriate way. So to think about that a little bit more, let's look at what types of materials make up the medical implants that are currently used in people. So first we have a dental implant. It's made of a stainless steel stem that gets inserted into the jaw and a porcelain ceramic top. Dental implants are, as far as we know, the very first type of medical device that people developed. Civilizations over 4,000 years ago were using different types of engineered materials in dentistry. Things like gold, ivory, wood. Here's another medical implant that's quite common. This is a hip joint, typically made from stainless steel or titanium alloys, and often with a coating of a ceramic or a plastic to put in between the articulating surfaces. This is a slightly less common device. This is a synthetic blood vessel. It's made from polymeric fabrics and textiles, things like nylon, polyester, or Gore-Tex. This is a pacemaker, a wonderful example of multiple types of materials coming together, all packaged within a metal case. And then this is just a tremendous feat of engineering. This is a completely synthetic heart that can be used in patients with critical end-stage heart disease, when they're not a good candidate for an organ transplant or other types of interventions. Now, those materials are cool, but they're the same materials that would be found in your golf bag. And this being beautiful San Diego, I'm guessing we have some golf enthusiasts in the audience. You may know that golf clubs started out being made from wood, just like our very first medical implants, teeth, and prosthetics were made from wood. Modern day materials now have entered into the golf place, right? You might have a stainless steel club that's your iron. For your driver, though, you might use a titanium alloy. For the same reason, you might choose to have titanium alloy for your hip implant, right? It's a much lighter material, right? A lighter density. So it doesn't weigh as much when you walk around with it. Even the raincoat that you might have stuffed into your golf bag, because everyone knows it doesn't rain in San Diego, that material, that textile, is virtually identical to the fabric that makes up synthetic blood vessels. So those materials were designed for different types of applications, not for use inside the body. Yet they do a remarkable job at replacing certain mechanical functions inside the body, but they can't communicate a chemical or biological function with cells. So let's look at what tissue normally would be. So tissue is a hybrid, a composite material of cells, which are stained purple in this image, and a material which is pink in this image. The material is there both to organize the cells, to put them in the proper structural rearrangement, but then also to give chemical information to those cells, giving them instructions, telling the cells what to do. This observation that tissue is made up of cells plus material is what led to an idea about 30 years ago that we could do tissue engineering, where if we take cells and we combine them with an engineered material in a petri dish in a laboratory, maybe we could create a medical device that was actual tissue. And this does work for some tissues and some organs. In fact, skin, which is what this image is of, was the first tissue engineered product to enter the healthcare market, and it was developed here in the San Diego area. So what type of materials should we use then if we want to design new types of tissues and organs? So in my laboratory, we take inspiration from the material that's normally found in our tissue, which is primarily protein. So we use biotechnology to create our own engineered proteins and tweak the protein so that it can give the proper chemical and biological instructions to the cells that it's meant to interface with. So how do we do this? We first decide what type of protein do we want to make. And then we encode that protein in a piece of DNA. That synthetic piece of DNA is then inserted into a host. In my group, we use helpful bacteria as our host. The hosts are then grown in a liquid media, much in the same way you would ferment beer. They make multiple copies of these genetic instructions, and then they read the genetic instructions to make a new engineered protein. We can then harvest that protein, separate it out from the rest of the fermentation mixture, and form a new material with the proper structure that we want it to have. For example, here I'm showing a scaffold with interconnected pores that would be a surface through which cells could grow. Here what I'm showing are some neurons or nerve cells that are growing within our engineered protein material. If we zoom out a little bit, we can see that these neurons really are forming a three-dimensional network. They're forming Stanford connections. And this means that they have to be interacting with the material. They're able to remodel the material. They're able to get the proper instructions so they know what to do. This is just one of the very first steps down a pathway of being able to create more complex medical devices that begin to look more like our natural tissue to replace not just the mechanical functions of diseased and injured tissues, which we're quite good at doing now, but beginning to think about replacing some of the chemical and biological functions in our tissue as well. Thank you.